Today, we are going to tear down and completely rebuild our understanding of what an operating system can even be. We're diving deep inside the architecture of SexOS, a really radical design that basically throws out decades of conventional wisdom, all in the chase for ultimate performance and security.
And, the folks behind this project are not shy about their goals. This quote, it's from the final release note of their roadmap. I mean, that is an incredibly bold claim to make. So to even begin to understand how they could back that up, we have to look at the unique, kind of wild architectural choices they've made, starting right at the very core.
So here's our roadmap for today. We're going to cover what makes this OS so incredibly different. We'll start with its tiny kernel, then its single massive address space, and the clever hardware trick it uses for security. Then we'll get into its everything as a server philosophy, and finally, the grand vision that ties this whole thing together.
All right, first up, the kernel. With SexOS, it's all built on this philosophy where less is genuinely, absolutely more. It all starts with something called a microkernel. Now, unlike the operating system you're probably using right now, a microkernel does the absolute bare minimum. You can think of it like a tiny, super secure foundation for a building. It only handles the most critical jobs, like basic memory and communication, and it pushes everything else, and I mean everything, out into less privileged areas.
And when I say tiny, I really mean it. The goal here is a trusted computing base. That's the part of the system that absolutely must be perfect, of just 5,000 to 8,000 lines of code. To put that in perspective, that's minuscule. The security implication is just huge. A smaller code base means a much, much smaller attack surface, fewer places for bugs to hide.
And this slide just lays out the difference perfectly. On the right, you've got your typical monolithic kernel, like Linux. You're talking tens of millions of lines of code for drivers, file systems, networking, all of it running in the most privileged space. A bug in your graphics driver, the whole machine could go down. But on the left, with SexOS, those exact same services are just regular programs. If a driver crashes, who cares? It doesn't take the whole system with it. Okay, next up, let's talk about memory. This is where SexOS gets really interesting. It just gets rid of the walls between processes and puts them all in one giant room. And the performance implications are massive. This concept is called a single address space. So in a normal OS, every single program gets its own private little memory map. When the OS switches from your browser to your music player, it has to do this slow, clumsy dance of tearing down one map and putting up a whole new one. With SexOS, there's only one map. That's it. Every single piece of code, all the data, everything in the entire system lives in one enormous 64-bit address space. So what's the big deal? Well, it's all about speed. By never having to switch those page tables, you get rid of a huge amount of overhead. You stop forcing the CPU to flush its critical address translation caches, which is like making it forget all its shortcuts. This makes it possible to have incredibly fast zero-copy communication, where one process can hand data to another without the kernel needing to slowly copy it all. The result? Absolutely lightning-fast communication between all the different parts of the OS. But hang on a second. If everything is in one big shared memory space, what's to stop a buggy program from scribbling all over another program's critical data? I mean, this sounds like a security nightmare, right? Well, SexOS has this really elegant solution, and you won't find it in software. This is the million-dollar question, isn't it? How do you get all those amazing performance benefits of a shared space without completely throwing away the isolation and security that we've relied on for decades? And the answer is pretty cool. It lies in a modern hardware feature called Intel Memory Protection Keys, or PKU. So instead of building these slow, complicated walls out of software, SexOS just leverages a security mechanism that's built right into the silicon of the CPU itself. Okay, so here's how this magic trick works, and it's brilliant. First, every little page of memory gets tagged with one of 16 different keys. Think of it like color-coding your files. Second, there's a special register in the CPU that acts like a keyring, and it holds the keys that the currently running code is allowed to use. And third, this is the best part, the CPU itself enforces the rules. If a program tries to touch memory that's tagged with a key it doesn't have on its ring, the hardware just instantly blocks it. All of this gives you super fine-grained protection with literally zero software overhead. It's security for free. So we've got a tiny kernel and a really fast, secure memory model. But how does this actually become a usable operating system? How do you do things like read files or connect to the internet? Well, remember how that microkernel pushed all the services out? In SexOS, the philosophy is that
Everything is a server. Your storage driver, your file system, your network stack, none of them are special kernel code. They are just normal programs running in their own little sandboxes, called protection domains, and each one is protected by its own hardware memory key. This makes the whole system incredibly modular and robust. And here are just a few of these key servers. You've got Sext, which manages all the memory. Then there's SexFiles for the file system, and SexDrive, which is a user space driver for your super fast NVMe storage. Each one is a totally separate, isolated server. So what this means is you could, for example, restart or update the network driver, SexNet, without ever having to reboot the entire computer. It's pretty amazing. So the obvious question is, how do all these separate little servers actually talk to each other to get any work done? Well, they use a custom super high-speed messaging system called Protected Procedure Calls, or PDX. This is the glue. It's what takes advantage of that single address space to let all these servers coordinate and pass data back and forth incredibly efficiently. A tiny kernel, a single address space, hardware isolation, and this whole symphony of servers. Okay, let's step back for a second and look at the big picture, the grand vision that all these architectural choices are building towards. This right here is the ultimate goal. This whole architecture, it wasn't just designed for a single machine. It was designed to treat a whole cluster of machines, what they call a sex node, as one single unified computer. That fast, secure communication we talked about, it's not just for processes on one box. It's designed to extend seamlessly across an entire network. So to wrap it all up, the entire design really rests on these four pillars. You've got minimalism from the microkernel, which gives you a tiny, secure foundation. You've got speed from the single address space, which just gets rid of those old bottlenecks. You get hardware-enforced security from Intel PKU at basically zero cost. And finally, you get incredible modularity from the server-based design, making the system super robust and flexible. And all of this brings us to one final, really big question. For decades, we just accepted that memory protection had to be slow. It was a given. But now, with new hardware features like these protection keys becoming standard in modern CPUs, it forces us to ask, is this radical, single address space architecture, which used to be just a niche academic idea, actually the blueprint for the next generation of all operating systems?